So I'd like to introduce our next speaker, which is sort of a favorite of the Weather and Climate Summit. Dr. Jennifer Francis from Rutgers University is going to talk about sort of the wacky weather that we've been experiencing all over the place. It's a global phenomenon, and how that might be impacted by changes in the Arctic. So let me just give you a little bit of background video for Jennifer Francis, and then she'll kick right into the presentation, so take a look.
What can we see happening with regard to extreme weather events?
Well, we're seeing a general increase in all sorts of extreme weather events. Some of them we're expecting because as the globe warms up, we expect to see more heat waves. It's kind of straightforward. But as the globe warms, we also know that there'll be more water vapor in the atmosphere, and we are definitely detecting that. And that tends to lead to heavier precipitation events, and we are definitely seeing those as well, especially in places like the eastern part of North America. But in addition to those expected weather events, we're also seeing an increase in the kinds of extreme events that are related to very persistent weather patterns. So things like drought, for example, persistent storm patterns, persistent even nice weather patterns. And this is the kind of extreme event that we're thinking has a connection to the rapid warming that's happening in the Arctic. So the jet stream is this fast-moving river of air high over our heads, up near where the jets fly, and it creates our weather that we feel down here on the surface. So not only does it separate the cold air to the north from the warm air to the south, but the waves, the north-south waves in the jet stream, are what create the storms and also the nice weather. So anything that changes those waves in the jet stream is going to affect those weather patterns that we experience. So as the temperature difference between the Arctic and the areas farther south gets smaller because the Arctic is warming so much faster, the winds of the jet stream are getting weaker, and that causes those waves to get larger, and those larger waves move more slowly. And so that means that the weather that they create also moves more slowly. So if you're in a nice weather pattern, it lasts longer. If you're in a stormy weather pattern, you get more storms.
All right, well, good morning, everyone. And I can't tell you how fun it is to be back here in Breckenridge. When I got the email from Dave Jones several months ago inviting me to come back here, I thought about it for maybe 1 nanosecond, whether I'd come or not. And there are many reasons for that. One, the most important one is because the people who come to this conference are just fantastic. And it's been a real treat to get to know some of these really terrific people that are delivering weather information to so many people every day and working really hard on that. The second reason is because the skiing here is so awesome, and I just love coming to Breck, and it's just a fantastic week. And if any of you are thinking of a ski vacation, I can highly recommend this place. It is absolutely terrific. So the last reason is actually more about me, and that is there has been literally a blizzard of research on this topic connecting crazy weather with changes in the Arctic over the last few years. I mean, this is a very new research topic, really only 3 or 4 years old. And there are now people working on this all over the world. I get papers to review every week, and just trying to keep up with the fast pace of this topic is a real challenge. So coming here forced me to really try to synthesize all this work that's been done and to try to put it together in a story for you all to bring you up to date on what's been going on around the world on this research topic. So let's get started. First, let's look back to a nightmare from last winter in Boston. I have a lot of friends and family who live in Boston, and last winter they were getting to the point where they were blaming me for what was going on in Boston. It was ridiculous. And I think, we might be looking at pictures like this in a couple of days for DC. I think people all up and down the East Coast are literally panicked that we're going to see a winter like last winter happening again. And there's maybe some reason to think that that might be the case. But a good friend of mine who took a little sympathy with me in my plight with these people blaming me for what was going on, sent me this cartoon. And I think it applies quite well today and probably this week going forward into this winter. So it seemed to sum things up pretty well about how people were feeling about this extreme weather that Mother Nature's been throwing at us these last couple winters. Oh, okay. All right. Technical difficulties with earrings. Haven't had that one before. But you know what? We don't have to look very back in time very far to see a very different picture. So the last 2 winters, we've had drought, warm conditions in the west, cold, snowy conditions in the east. Go back to 2012, this January through March, extreme conditions that we saw back then. Those red states are all broken records for heat. So just keep in mind that 1 year does not make a pattern. And we see these different changing conditions from 1 year to the next. So what was in common between these 2 different situations, though, was how persistent they were. That word persistent is going to come up a lot today. But we are not alone here in the United States. And we heard a lot about extreme events from Lance Rothfuss yesterday. And we know that Mother Nature's been throwing the book at us here in the United States, but it's not just us. So in the UK, the last couple of winters, and including just last December, has been seeing extreme events like they've never seen before, just storm after storm after storm. We know parts of Japan have been seeing an amazing amount of snow. Even places where they expect a lot of snow. In this particular winter of 2012, it was ridiculous. I don't know how they keep that road plowed. I think this picture could be used for that, maybe in a couple of days. Yep. We heard also about the flooding that's been happening all around just this past month in our country, well, actually earlier in January in the Mississippi Valley area. Incredible flooding. You don't expect to see flooding like that in January in the Mississippi Valley. But it's happening all around the Northern Hemisphere. We've got lots and lots of examples of unprecedented flooding. And then, of course, we heard a lot about the drought from Tim Brown a couple days ago. The last couple years have been really tough. We can see images like this. And, it's raining there this winter, thank goodness, but it's going to have to rain a whole lot to make up for the drought that we've had over these last few years. And we, as scientists, are not alone in keeping track of these extreme events. The insurance industry, for example, is really paying a lot of attention to this because, of course, their bottom line depends on how much money they have to shell out for these extreme events. So here's an analysis by Munich Re, one of the big insurance companies in the world, and they track the number of extreme events that have been happening around the world. And what's interesting is they break it down into categories. So going back to, looks like 1980-ish or so, the red bars there are extreme events that have to do with geophysical extremes. So things like earthquakes and tsunamis. All the other colors, the greens, the blues, and the oranges there, are all having to do with weather. And what you notice is that those geophysical events are not changing over time, but those weather-related ones are. So the extreme weather events that I'm talking about that are related, I believe, to changes that are happening in the Arctic have something in common. And they are that they're all related to very persistent weather patterns. There's that word again, persistent, stuck. That's what people are perceiving. Their weather is not changing as often as it used to. And when you have a weather pattern that lasts a long time, that can lead to an extreme event. So people are noticing this. They feel this weather changing in their own backyards. It's affecting them. They're seeing it on the news. This crowd is putting out all kinds of information about these very unusual weather patterns that have been happening around the world. People are wondering whether there's some connection to climate change, in particular human-caused climate change, because it's just not the same as it used to be. And so this question, is it related to climate change or not, is getting a lot of attention in the research community now. And it hasn't been that long that the scientists who are studying this have been comfortable answering this question. But I think most of us now are quite comfortable saying there is a link to climate change. They're not all obvious, they're not all totally understood, but certainly we're seeing an effect of climate change on affecting these extreme events. So let's step back a little bit before we get into the details here and just kind of set the stage, remember where we are. We all know that carbon dioxide has been increasing lately over time. We know that humans are doing it, and we know that the amount of carbon dioxide in the atmosphere now is around 400 parts per million. I have here that it's the highest it's been in the last 800,000 years at least, but last night we heard from Jim White an update on that number, and it's more like 4 to 5 million years ago. Is that right, Jim? That the amount of carbon dioxide in the atmosphere has been as high as it is right now. And back then, the Earth was a very different place. Sea levels were many feet higher. There was very little ice left in the Arctic. So this is the path that we're on. We've already got the carbon dioxide in the atmosphere. The Earth is starting to catch up with this temperature. As you can see, the carbon dioxide is shown in the blue curve on this graph, where the temperature is in red. And you can see that it's really starting to respond to this high level of carbon dioxide in the atmosphere. But we also know that the warming that's happening around the globe is not happening uniformly. This is showing how the temperatures have changed in the last decade or so from what we consider normal. And what you notice is that in the high northern latitudes up in the Arctic is where we're seeing the biggest warming occurring. We're going to talk a whole lot more about that. But let's focus in on just the winter season here. This is actually now trends in temperature during the December, January, February timeframe over the last decade or so. And what you notice is that we see again that high in the Arctic, those red colors are telling us where those temperature trends are the largest, where it's warming the fastest. But interestingly, you also see this blue blob over Central Asia, where it's actually been cooling in the winter over time. And you can't see it very well perhaps here, but it's also bluish over North America. So over the United States, especially Eastern North America. So there's a lot of differences in where these temperature trends are occurring and reasons for that. And we'll be talking about that later. And as we know, as the temperature of the Earth rises, so does the amount of water vapor in the atmosphere. That water vapor is very important because it provides a lot of fuel for storms that develop. So any storm that develops now is forming in a different environment from what it used to because it has this extra energy to tap into. Water vapor itself is a greenhouse gas. So as we increase that water vapor, it's accentuating the effect of the carbon dioxide that we're putting in the atmosphere, adding to this greenhouse effect of trapping heat to the surface. And we also know that that extra water vapor is contributing to heavier precipitation events. And we see this in the data looking over the last decade or two compared to the 20th century, and we see that the frequency of heavy precipitation events has been increasing quite dramatically over time, especially in the Northeast. All right, so let's start talking about the Arctic now. It's been described as unraveling, the changes that are happening up there. We heard a lot from Laura Koenig earlier in this week about the changes that have been happening in Greenland. And just to remind you what she talked about, or if you weren't here, what we're noticing, among other things, is that the area of Greenland's surface, remember Greenland is covered by a very thick ice sheet, the surface of that ice sheet has been melting in increasing areas. And so looking back to 1992 on the left here, what we see is that orange area around the edges is where that summer the surface experienced some melt, sometime during that summer. Only a decade later, in 2002, we see that area expanding tremendously. Only a couple years later, in 2005, again, we see a big increase in that area of Greenland that experienced some amount of melt. And then we jump to 2012, and we see that nearly the entire surface of Greenland underwent some melt that year. And that was the first time that had been seen in at least 150 years. And before that, it was a couple thousand years. This is very concerning because as that melting occurs in Greenland, because that ice is on land, that extra meltwater is going to go straight into the ocean and contribute to sea level rise. And we can also look at how this is showing up in the amount of total ice on Greenland. Going back to the early 2000s where we first had the kind of satellite data that we can measure this quantity with, what we see is a very steady decline in the mass of the ice sitting on top of Greenland. This is a very clear signal of climate change. There's really nothing you can dispute about this. This is happening. This is a direct contribution to sea level rise. So this one is a little more controversial, perhaps. We talked about this the other day when Phil was talking about hurricanes. And what we're noticing is that in the North Atlantic, we have, here's Greenland in the north and North America on the left here, this big blob of cool ocean temperatures just south of Iceland and these very warm temperatures over along the east coast of North America. And there has been a paper that came out very recently suggesting that this meltwater from Greenland that I was just talking about is contributing to this blob of cool temperatures south of Iceland there. So we're going to talk about that as a potential effect on weather patterns. But it appears to have at least some link back to the Arctic through the meltwater on Greenland. And also we heard from Laura earlier this week that the glaciers all around the world are in rapid decline. Here's an example of one in Austria, looking at a photograph from back in 1875, comparing it to about 125 years later, what that same glacier looked like. And this is not something unique to European glaciers. If we look at the mass of glaciers all around the planet, what we see here is a general decline going back to the 1960s. You can see that there are curves here for Patagonia in South America. There's Asian glaciers. All of the glaciers around the globe are losing mass. Again, this is contributing to sea level rise. And the other form of permanent ice up in the Arctic is called permafrost. And this is the moisture that's in the soil that's frozen in a permanent basis. It doesn't thaw during the summertime. There's been a lot of work looking at how the permafrost, especially in northern Alaska, has been changing over time. So here we have a map of northern Alaska. Those green boxes are showing boreholes where they monitor the temperature of the soil going down into the soil and how those have been changing over time. And this very northern part here where there's pretty much all permafrost, I think north of that blue dashed line is where we see permanent permafrost. These curves here are showing us how the temperature has been changing in those boreholes. So going down the graph is going deeper into the soil, and each of those colors represents one of those stations there. And what you can see is that all of them are getting warmer over time, going back to, say, the 1980s or so. This is painting a very consistent picture of we're losing these permanent forms of ice in the Arctic. The story is very consistent. And then there's the sea ice. Well, we can actually get a pretty good idea of what's been going on with sea ice back about 1,500 years. And this is based on proxy evidence by looking at the sediments at the bottom of the Arctic Ocean. And depending on whether there's ice or no ice on the surface of the Arctic during the summertime, different organisms live in the water column. And so as those organisms die, they fall down into the sediment. And so by tracking those over time, we can determine pretty reasonably how much ice there was covering the Arctic in the summer going back quite a ways. And what you notice is that there's some wiggles even over centuries, but it's pretty steady until we get up to the modern record. And what you can see is that the changes that have been happening in the last few decades are literally in uncharted territory. We've never seen anything like this going back as far as we can look. But this data doesn't include what's been happening just in the last decade or so, in particular in 2012, when we set a new record for the least amount of sea ice on the Arctic Ocean. And if we put that information on this graph, that's where it sits. It won't even fit on this graph. So you might have heard that the sea ice since 2012 rebounded, it grew back, everything's fine, we have nothing to worry about. All right, well, let's check out 2013 and 2014, see how that fits on this graph. Huge rebound, right? Nothing to worry about there. Well, we can put 2015 on here too. We just were able to assess that over this last summer. No rebound, all right? This is, if you've heard that story, don't believe it. So the next thing I want to do is just give you a little, show you a little animation that shows how the sea ice has been changing just over the last couple of decades. This is an animation that was put together by NOAA and NASA together. And as it gets started and rotates up over the North Pole, I'll get you oriented here. So here we are, looking down on the North Pole. Whoop, stop. Oh, it's not going to stop. All right, so what you're looking at here is an estimate of ice age. Let me try to stop this so I can answer your question.
You can roll.
Okay.
Francis Howard Bernstein, WUSA, Washington. How are they indicating or how are they detecting what's old and what's new? How is that done?
Well, that's what I was going to tell you while I was waiting for this
Sorry.
to... Let's do it this way. Okay. So the way this is done is using satellite information and looking at features in the ice, so things that they can recognize as a feature. And so through time, you track those features and you keep track of how old it is, how long have you been able to see it. So the age of the ice then is very closely related to how thick it is. So the longer a piece of ice is hanging out in the Arctic, the thicker it tends to be. So this is kind of a proxy information for ice thickness. So where we see these white colors here are where the ice is old and therefore thick, and where it's blue, it's where it's thinner. So this animation then is going to go through time. We're already up to 2005 here, which is okay. And what you're going to see as you look at this animation proceed, there's a couple of things. First, you're going to notice that every year we see an expansion of the ice in the wintertime and a shrinking back in the summer. So it goes through this cycle. It about doubles in its aerial coverage during the wintertime. You're also going to see how the ice tends to move in a clockwise direction. And this is just responding to the climatological wind direction that occurs up in the Arctic Ocean. So let's put this back in motion. So again, we're already up to 2006. And I don't know if you remember what it looked like in the beginning, but there was a whole lot more of that white ice there then. And here we are coming up to almost present time. And what you see is that there's almost none of that thick white ice left. The Arctic is now dominated by much thinner ice, and it's very broken. It's very vulnerable to any anomalies in winds or ocean currents. So what we're seeing is an ice cover that's very, very different from anything we've seen before. Okay. So why do we care about...
Hey, sorry.
Yeah, sure.
Mike Richardson, WSI. I just had a question on that time series you showed on
Yeah.
the previous slide. Is that using an average of the actual year, or is it more focused on the summertime sea ice?
No, it was all year round. So that's why you could see it growing in the winter and shrinking back in the summer. So it goes through all the months.
So the actual time series where you showed 2012 plummet down to like 2...
Oh, no, that was summer.
That was summer. Okay.
Summer ice cover.
Thank
yep.
you.
Mm-hmm. Which is when it's at its minimum extent. Okay. And that in the summertime is when we're seeing the biggest declines. And the reason for that is because during the winter, the ice grows, but around most of the Arctic Ocean, it's confined by a coastline. So it can only grow so far, except in a couple places, in the Pacific, over near Alaska, and over on the Atlantic side, just west of Norway. And we'll get into that a lot more soon, too. So one of the reasons we care so much about the fact that the sea ice is declining so much is that ice is white, right? White ice and snow reflect most of the sunshine that hits it. So here we have the white here looking down on the North Pole. There's Greenland down at the bottom. This white ice is the cover that was existing in summer 2012 when we had that new record low. The pink line around there is how much ice there was on average during the previous 30 years. So you can see how different 2012 was compared to what it had been just in the years before. So again, the reason we care is because this ice is very reflective. Most of the sunshine that hits it gets reflected right back to outer space. And now that we have so much less of it, much more of that sun's energy is going into the ocean, warming up the Arctic Ocean. And that is one of the main reasons why we're seeing the Arctic warming so much faster than anywhere else on the planet. The Arctic is warming 2 to 3 times faster.
Dr. Francis,
yes, sir.
Joe Virgo for WTAJ. One of the things that always bugs me a little bit is the albedo of ice is very high.
Yes.
The albedo of water is almost as high when the sun is at a low angle, and isn't the sun, I mean, it's hitting a peak of only 23.5 degrees. So at times, is this being a little overstated?
No, because...
Well, I mean, that's why I'm asking and giving your...
Because that water albedo that you're talking about is only true when it's calm. If there's wind, it's rough. And so the albedo plummets when there's wind. It's not calm very often up there in the Arctic. So most of the time, the albedo is very, very low, below 10%.
Okay.
Probably more like down around 2%.
No,
okay? Yeah, any more burning questions like that you have?
No,
you know that you've always wondered? Yeah, let them rip.
Burning the inevitable?
Okay, so we call this warming of the Arctic. You've probably heard it called Arctic amplification, polar amplification. I like to call it amplified Arctic warming, so this AAW. And we know that this is happening on an annual basis, but it's also very different depending on which season you're talking about. So here, what I'm showing is a metric of this amplified Arctic warming going back to the late 1940s. And a positive number on this graph means that the Arctic is warming faster than mid-latitudes. All right? So we've got these 5 different lines on here. Brown and blue are autumn and winter. These are the seasons when we're seeing the biggest warming in the Arctic relative to mid-latitudes. But you can also see it starting to emerge in spring and summer as well. But what I also want you to notice is just how recent this effect has been occurring. It's really just the late 1990s. This presents a big challenge because if we're trying to understand how weather patterns are responding to this new signal of Arctic amplification, this doesn't give us a lot of time in the real world to try to figure out what these responses are and to get robust statistics. So just keep that in the back of your mind. All right, so let's move into the meat here and talk about why this amplified Arctic warming is such a big deal and how does it affect our weather down here in mid-latitudes.
Dr. Francis, sorry
Yep.
to interrupt again. Mike Fisher, WSI. It seems like that acceleration of the warming has happened since 1997, which was right after the super El Nino, right? So there was a major climate shift following that event, and we are currently in another super El Nino.
Mm-hmm.
Do you think there would be any more, do you think that there's a chance there could be another climate shift following this El Nino into another level in this type of framework?
There's a chance. I think the El Nino definitely contributes to it. I mean, I don't see a big jump at 1998 when I look at this graph. Certainly,
there's a yellow line. That's kind of why it looks like.
Yeah, I mean, it kind of draws your eye there. I mean, I just put that there. You know, that's really when all the seasons basically went above the 0 line. Mm-hmm. There are a lot of competing effects, actually, in terms of what affects this amplified Arctic warming. I'll be talking about the PDO, for example, later, the Pacific Decadal Oscillation. And we think that actually might have a bigger impact because El Nino is a short-lived phenomenon, right? It's only a year. Whereas these ocean temperature shifts that last much longer, we think are having a much bigger impact on the magnitude of this amplified Arctic warming.
Yeah. And
Yeah. Yep.
Jim, while you mentioned Colorado, just a quick comment on that. There is a very good relationship between snow cover and this amplified warming. So the physics actually makes sense. After 97, you start to see a real drop-off in snow cover in the northern hemisphere. And that's
In the spring. In the spring.
in the spring, yeah.
Yes.
And that's consistent with what you're seeing. Now, why that timing occurs is an interesting question, but the fact is that's when you start to see a pretty big drop.
Yeah, and in fact, I'm not going to talk about snow cover, but the change in snow cover on high latitude land areas is even bigger than the change in sea ice. It's huge. So we think that is probably playing into more the summer impacts of Arctic change on weather patterns. Okay, so again, why is this such a big deal? Well, in my view, it's all about the jet stream. And so what I want to do is go back to your Weather 101 course that you had just a few years ago for some of you, I'm sure. And you might have seen a diagram like this that basically illustrates the main circulation systems of our hemisphere. So on the right there is the equator, the tropics, and as you go towards the left, you get up to the North Pole. We have these three main circulation systems in the northern hemisphere, same thing in the southern hemisphere, where we have basically the main driver is all of the extra heat that gets dumped into the tropics. And somehow that extra heat has to get redistributed up to the mid-latitudes and to the poles. Otherwise, the tropics would just get warmer and warmer and warmer, and the poles would get colder and colder and colder. So it's this balance. And the way that's done is through the wind systems of the Earth. So here we have, in the tropics, we have all this heat and rising air, big thunderstorms, and that the next cell going northward is the feral cell, and where those two meet, we see this big difference in temperature between the tropics and the mid-latitudes, which creates that subtropical jet stream. And then as you continue to go forward, we have the feral cell and the polar cell, and again, big difference in temperature between those two major air masses, and that drives what we call the polar jet. So these big latitudinal differences in air mass temperature are really what drive these two major jet streams. But what's happening? All right, we know that this amplified Arctic warming is happening. That is causing the air in the Arctic to expand. That's raising the tropopause. Everybody remembers what the tropopause is. Below the tropopause, the atmosphere gets colder with height in general, and then above the tropopause is where the atmosphere tends to get warmer with height. It's this major division in the atmosphere. So as that Arctic air warms, as I was just telling you, this Arctic amplification or amplified Arctic warming, the tropopause there and the whole atmospheric column is being pushed upward. And I'll show you some actual data that shows that. But in the mid-latitudes, where the warming is much smaller, the change is also much smaller in that tropopause height. And so this difference in temperature between these two zones is getting smaller. And what does that do? It weakens that polar jet. All right? But we have a competition going on, and this is a topic of a research topic that's really hot right now, and that is we also know that the upper levels of the tropics are warming rapidly as well. So what's happening with that then? We're getting an increase in that tropopause in the tropics, and that is actually strengthening that poleward gradient and causing the subtropical jet to get stronger. So there's this tug of war between what's happening with the polar jet and the subtropical jet. And I just want to raise that in your awareness because there's a lot of research coming out on this topic now. But we're going to be talking mostly about the polar jet, so the barrier between the mid-latitude air masses and the polar air masses. So as I said, there's been a lot of work going on this topic of how the Arctic is affecting mid-latitude weather. And I've tried to boil it down by putting it into three basic categories. The first is the one that we've heard about before, the fact that we're reducing this poleward gradient, and that's leading to a weakening of the zonal winds. But we're learning a lot of detail about how these weakening zonal winds are playing out in different regions and in different seasons. So I'm going to try to bring you up to date on what some of those new mechanisms that are emerging are. The second one I call It Takes Two to Tango. And I'm showing here a map of surface temperatures in the Arctic. And what you notice is that we've got the Pacific over on the left, so there's Alaska over on the left, and the Atlantic side over on the right with Norway. And we see these very different year-to-year patterns of surface temperature changes in the Arctic. This comes into our It Takes Two to Tango. So stay tuned for that. And number three is this probably more controversial idea that the Arctic is perhaps causing these sea surface temperature changes in the Atlantic, which I think may be affecting the jet stream there. So these are the three basic categories. The first one has the most stuff in it. It's going to take me the longest, and then we'll talk about the other two as well. So keep an eye on the upper left corner. That'll tell you which category we're in. So first, looking at how this amplified Arctic warming is affecting is causing weaker zonal winds. We can measure this. What I'm showing you here is a cross-section from 40 north to 80 north, looking upward in the atmosphere, and how the temperatures have changed on an annual basis in this last decade and a half or so. And what we expect to see is that the warming is largest up in the polar regions, in the high latitudes where we're losing the sea ice, but it's positive just about everywhere through the atmospheric column. But what happens is, as those lower layers of the atmosphere warm, they expand, and as we already talked about, that pushes up those height levels in the atmosphere. So what we see is, instead of the biggest impact being by the surface in terms of temperature, in terms of height anomalies, it actually gets larger as you go upward in the atmosphere. So, and you can imagine now how this is affecting that poleward gradient, right? As you go from south to north and look at these changes in the height levels, we see this translated to what's happening to the zonal winds. So these purple colors here are showing you how the zonal wind changes are corresponding to these changes in the height field. But as I said, there's a lot of regional variability and a lot of seasonal variability in how these changes in heights and winds are playing out. But one thing we do know is that the real world is telling us something, and the models are confirming it. So this is a very recent paper that came out where they took a very sophisticated atmospheric model. They presented it with the 2012 ice anomaly. I showed you that was the lowest ice we've ever seen. On the left there is how the atmospheric temperature, or this is the height response to that, the 500 millibar height response to that loss of sea ice. Those red colors are showing you how that 500 millibar height level has increased. And then on the right is the change in the zonal winds. So the models are capturing this response as well. That's always good. So in terms of regional variability now, we can again go back to observations. And what we're looking at here are anomalies in the thickness, the 1,000 to 500 millibar thickness field. So that bottom half of the atmosphere, how the thickness of that layer is different during this period of amplified Arctic warming compared to the 30 years before. These red colors are showing you where the thickness of that layer is much larger now than it was back earlier in the time in the record. So you can see, though, that there's areas where this thickness anomaly is much stronger. It penetrates farther south, a lot of regional variability around the northern hemisphere, and this is in the fall. So if we now look at how the zonal wind fields changed at the same time and place, the purple and blue colors here are showing you where the zonal winds have decreased. And with your eye, you can see very easily that those areas where the zonal winds have decreased match very well where we see that poleward gradient weakening because of that thickness change in the north. So wherever the thicknesses are changing faster in the north, that's where we see the weakened gradient, and it shows up very clearly as weaker zonal winds. We can plot this. Yeah?
So we would, by looking at that, infer that the western Atlantic and eastern U.S. have had a significant slowing in the jet stream during that analysis, the period of that analysis.
The zonal wind component, yes.
Yeah. Okay.
During this period, yep. Jim, did you have a question?
No.
Just stretching back there. So we can look at this a little more quantitatively And for every single grid point here, and I should mention this is from NCEP reanalysis data, we can plot how the thickness gradient has changed at every grid point versus how the wind speed has changed at 500 millibars. Okay? So that's what this scatter plot is showing you. The black dots there are where the winds are strongest, the total winds. So that's picking out where the jet stream is, basically. So what you see is a very robust relationship showing you that where the gradient has gotten weaker, we see a weakening of the winds. So, yeah?
Hi, Phil Klotzbach, Colorado State University. I just was wondering, given the cooling that we've talked about in the far North Atlantic, wouldn't that almost cause the opposite effect over the North Atlantic?
Totally. And we're going to talk about that later.
Okay, perfect.
So this doesn't include that, because that cool pool showed up
about 2 years
at the end of 2012. Is that right? End of 2013. End of 2013. Yep. So that's, that's a whole new piece of this puzzle. Yep. That's not included in this data. So why do we care so much about this polar temperature gradient and these weakening winds? So I think I've showed you that we definitely see this weakening gradient. We know that a weakened gradient causes weaker west to east winds. We now have a new paper that just came out that theoretically shows that when you have weaker zonal winds in the jet stream, you have larger wave amplitudes. This is something that's been missing for a long time. This paper is really important, I think, because it actually makes this theoretical link there. I think as meteorologists, we're kind of used to thinking about that. When you see a weaker jet on the weather maps, you tend to expect to see a more meandering jet. But it's always been kind of a, yeah, we think this is the way it goes. But this paper actually makes that theoretical link.
Dr. Francis,
yep.
When you have these larger planetary waves and you have a more amplified pattern, are they including in that study because that is also better transporting heat to the poles and cold to mid-latitudes? Is that a feedback mechanism that is speeding things along and warming the...
It's not necessarily the case, because when the jet is strong, we have more transient eddies, right? More storms when the jet is strong. Those individual storms, because they're baroclinic, they are very efficient at transporting heat northward and cold southward. It's doing the same thing, basically. When the waves get large, they tend to be more barotropic. So, you're basically, the winds are riding along the lines of thickness. So you're not actually getting very efficient transport of heat and moisture in these large barotropic waves, as opposed to the transient baroclinic storms. It's not obvious that one... Actually, I think transient waves have been shown to be more efficient and, really doing the job of mixing up the heat from the tropics to the poles. Okay, so we know when these waves in the atmosphere, and that's what these little schematics are showing, when the waves are small, they tend to move quite quickly from west to east. And when they get big, and we've all seen these on weather maps, they tend to get very sluggish, and they tend to either move slowly or sometimes even move westward. So if this is true then, that the warming in the Arctic is reducing this polar gradient, reducing the winds, making these waves bigger, or another way to say that is perhaps causing wavier patterns to happen more often, then the idea here then is that we should see more persistent weather patterns happening. That's sort of the grandiose hypothesis there. And of course, you all know, but just to make sure everybody who's watching here understands why we care so much about these waves, is that those waves are create the dynamics in the atmosphere that make what we call weather. And just to give you a little schematic of this, here's a typical jet stream. Looks a lot like what it's looked like for the last 2 winters prior to this one. So here's the schematic jet stream. First of all, you see that it separates the cold in the north from the warm air to the south. But what we also know is that different parts of these waves cause the dynamics in the atmosphere that create dry and settled weather, for example, where those winds are coming out of the northwest, basically. The air is sinking in the column. And where we find the part of the wave where the winds are out of the southwest. This is where we get the dynamics that tend to create the wet and stormy conditions like we're about to see in the East Coast right now. So that is all seemingly very simple and neat and very easy to understand, but when we look at the real jet stream, it's not simple. There's nothing simple about the jet stream. This is some real wind data that NASA has put together into a neat animation. I'm sure a lot of you have seen this one before. Where the red and yellow colors are, where the winds are really strong, you can easily see with your eye where the jet stream is. But what I want you to notice, a couple of things here as we go through it a couple times. First of all, just what an ungodly mess it is. There are like swirls of all different sizes and shapes and different places. And just try to imagine measuring any kind of changes that might be happening in this jet stream in terms of whether it's getting wavier or less wavy and where and that sort of thing. And you can also kind of see when those waves were small, they were whipping right across the North America, and then when they get big, they tend to be very persistent in their location. So this is the real world we're dealing with. And it's not a simple thing to try to understand whether we're seeing the kinds of changes that we are hypothesizing we should see. So this is really the question that we're trying to answer. Are we seeing either these waves getting bigger over time, or are we, another way to say it is, are these wavy patterns that we see anyway happening more often? So this is what we're trying to do. We're developing new metrics to do this, and I'm going to try to give you just a little glimpse of some of the research that's been going on lately. So one of these ways that we're trying to measure this is with this very simple metric called the Meridional Circulation Index. And it's dead simple. All it is the ratio of the north-south component of the wind to the total wind. Could not be simpler. Think about a wind vector. We break it down into its north-south component, which is the V, and the east-west component, which is the U. Now, I've just talked a lot about how we're reducing that west to east component of the wind because of the polar gradient getting weaker. So if you reduce just that west to east component, then you're going to, just through geometry, shift that vector in the wind. You're going to make it more meridional. And that's what this index measures. It's how meridional, how north-south is that wind. And we can apply that to reanalysis data. You can apply it to model output, any wind field you want. So let's go back to this wind anomaly field that I showed you a few minutes ago in response to those thickness changes. This is in the fall, and these are winds at 500 millibars and the anomalies in those winds. So we can apply that metric, that meridional circulation index, to this field, and what do we see? These red colors that you see here are where that wind vector has shifted over time to be more north-south. In other words, the winds have become wavier, or the pattern has become wavier. And where they're blue, it's actually become more zonal. And you can see with your eye that where the winds are weaker in the upper panel there, the blue and purple colors, is where we tend to see this index becoming more positive. And again, we can do this in a more quantitative way, and grid point by grid point plot the change in the zonal wind on the horizontal axis there versus the change in this index. And what we see very clearly and very statistically robustly is that when the winds weaken, we get a positive change in this index. So that's telling us that this is making this link back to the Arctic here. Weaker warming in the Arctic, weaker winds, more meridional flow. So another aspect of this, and this is some really good work that's come out of the University of Potsdam in Germany. They've been focusing more on the summer season and looking at how the weakening zonal winds in the summer are linked with extreme weather events over Eurasia in the summertime, heat waves and droughts in particular. And what they have found is that when the zonal winds in the summer are weaker, they tend to see more split jet configurations. And here's an example where these red and yellow colors are showing you where the strongest winds are. And this happened to be during the heat wave of 2006. It was a major heat wave there. And what they found was that when the jet splits, it tends to create a waveguide, what's called a waveguide. This tends to trap the waves in the jet stream and set up stagnant waves, basically. And so when this happens, it tends to lead to these very persistent, stagnant weather patterns. And if they looked back over time and looked at the months when these split jets occurred, which are the bars, and how those have been changing in frequency over time, the dates on each of those bars are particular extreme events that happened in Eurasia, so heat waves, droughts, flooding events. And also plotted on there is how this amplified Arctic warming has been changing over time. So this is a link that they've made during the summer season to extreme weather in the summer months. So another way that we've been trying to get at this question of whether the jet is taking on this wavier character or not is another very simple metric. Here we've got the 500 millibar height field looking on North America. This happened to be in January of 2014 when the polar vortex attacked us, and it kind of went viral over the internet. So what we're doing, though, is we're just taking one isopleth of the 500 millibar height field. This particular isopleth is chosen so that it's climatologically in the jet stream. So it's where the gradient is strongest, all right? So this is showing you which one we took. It tends to be 5,600 meters for those who like to keep track of those sorts of things. And all we do is every day we measure how far north and how far south this particular isopleth went in different regions, okay? Totally dead simple. And then whenever that distance, whenever that difference in latitude exceeded a certain threshold, and we've picked 35 degrees of latitude, then we call that an amplified wave day or a high amplitude pattern. And we just count those days and see whether those very wavy days are changing over time, different seasons, different regions. And just to give you an example of the result for the whole northern hemisphere here during the fall, and we plot this starting in late 1979, the green line there is showing you how the frequency of these high amplitude patterns has been changing over time. Clearly there's a big uptick. And also plotted on there is how the upper level wind speeds have been changing at the same time. And you can see they're very closely related to each other. We've done this in different regions, different seasons, and this seems to be a very robust linkage here.
Hey, Dr. Francis.
Yep.
I was just wondering, this is using NSEP and car reanalysis?
Yep.
Is there a reason why you stopped in 1980 and go into 48 where it begins? Or
Well, when we wrote up this paper, and the one before this in 2012 that kind of started this whole research topic, the reviewers complained that the data weren't as reliable going back before the satellite era, and so we've just kind of been sticking with that to avoid criticism. But I think, you know, at 500 millibars, I think the fields are actually very reliable. So I think you could very well go back in time. Yeah. Okay. So this is some new work that we've been doing, and I'm not going to talk about this too much, but I'm sure you all know what a block is. So this is when the upper level winds, basically the amplitude of the wave gets so big that sometimes that wave actually breaks and you get a separate eddy forming in the upper atmosphere. This is called a blocking high, and these blocks tend to be very long-lived. They tend to create very persistent weather conditions, and there's a lot of research going on to try to understand how these blocks are changing over time and whether, in fact, they are changing over time. So this is one blocking data set, and there are many ways to try to measure a block, how big it is, how strong it is, and different blocking data sets give you slightly different results. But what we've plotted here is going back to the mid-1970s, how this particular blocking metric has been changing over time in the Atlantic sector, which is where blocks are probably the most frequent of anywhere, over in the Pacific, and also over the continents. And what we're seeing that from this blocking data set is there definitely seems to be an uptick in the last couple decades in the number of days with blocks. So this is ongoing research. we're actually approaching this using a pattern recognition approach, and so stay tuned for some developments on that score. But these blocks are a very important part of our atmosphere. They're very difficult for the numerical models to both form and to dissipate, and so they present a real challenge for forecasting. Yeah.
My question, sorry. So is there a time constraint on the number of days that a block is considered a block for this type of analysis?
Yeah, and that's part of some of the differences between the blocking metrics. I think probably the most common number of days is 5.
Okay, thank you.
That I've seen. Okay, we're moving into group number 2 now of these mechanisms and hypotheses that are out there linking the Arctic to mid-latitude weather pattern changes. This is a new one that I'm talking about and starting to work on, and I call it the "it takes two to tango" hypothesis. And let me explain what I mean. So let's start by looking back in time to the good old days when we had lots of sea ice in the Arctic Ocean. Here we're looking down in the Pacific. You can see North America on the right there, and the Arctic was basically filled with sea ice. So let's say a wave in the jet stream came along. And, you know, they get positioned in different places depending on sea surface temperature patterns, and a lot of different things affect where the waves in the jet stream tend to set up. And when there was lots of ice in the Arctic, it really didn't have any impact on what was going on with these waves in the jet stream. But let's move forward in time to what's going on now. And you can see that north of Alaska there's a big chunk taken out of the sea ice. And as I already told you, when that happens, we tend to get a lot more solar energy during the summer getting absorbed into that open water that used to be covered by ice. And in the fall then, all that energy that was absorbed all summer gets re-emitted back into the atmosphere, and it warms the atmosphere in that location. So let's say a wave in the jet stream comes along. This is just a rough schematic, but it's basically what you'd expect to see in, say, negative PDO conditions. So the negative PDO is the PDO is a particular sea surface temperature pattern out in the Pacific. When it's negative, you tend to get cold water along the west coast of North America. And when that happens, we tend to get a wave in the jet stream that favors this location. When that happens, it has no effect. The sea ice loss has no effect on that wave because where the ice was lost and where the ridge is are not co-located. But in a positive PDO situation, we tend to get the ridge located roughly here. And this is what it's looked like basically since late 2013. There was a big shift from the negative PDO, which it had been for about 10 years, over to the positive PDO. So now what's happened is that extra warming from the sea ice loss in the Pacific sector now is causing that ridge to be intensified. All right? That's causing that ridge to get larger, and that makes it more persistent. Remember, those larger waves move more slowly. So this is what I'm calling it takes two to tango, because you've got to have not just sea ice loss, not just Arctic warming in a particular location, but you also have these factors that are natural. These natural variability factors that have to line up in just the right way for there to be an impact. So you have these two necessary factors, but neither one alone is going to cause this ridge, in this case, to be intensified and therefore more persistent. So that's the idea. Let's look at some research that seems to support this idea. So I showed you this plot earlier. It's the trends in the surface temperatures during the winter time in the last decade and a half or so. We see this area sort of northeast of Siberia. This particular area is called the Barents-Kara Sea, and it's one of the areas where we've seen the most sea ice loss occurring on a regular basis. And again, we see that cold trend area over Asia. Well, a bunch of people have been trying to figure out how we can get these cold trends happening in Asia and whether there's any connection back to this ice loss area in the Barents-Kara Sea. So here's the story. So we've seen this ice loss in this area very strong in some years, some more than others. And the idea is that when we get this it takes two to tango happening, we get the ridge forming in the same places where this ice is being lost. We see this ridge and you can see it's pointing with the arrow there. The ridge there is intensified. When you intensify that ridge in that area, the surface expression downstream is going to be a stronger surface high. The clockwise circulation around that high is going to bring more Arctic air down east of it, down into Central Asia. And what does that do? It cools Central Asia, and it depresses, it intensifies the trough over Asia. That amplifies that whole ridge-trough couplet. So then what happens if you increase the waviness of the tropospheric jet stream? That wave energy in the winter gets transferred up to the stratospheric jet stream, or the stratospheric polar vortex, and it tends to disrupt it. So instead of being relatively circular, as you see on the left, it becomes more elongated and potentially broken, as you see on the right. So that's because that extra wave energy is getting transferred upward into the stratosphere. And then what's interesting is that if you disrupt that stratospheric vortex later in the winter, see February now, this is like a memory mechanism in the atmosphere. That broken or disrupted stratospheric vortex retransmits wave energy back down to the tropospheric jet stream. And that perpetuates the waviness that was originally caused by the ice loss, or at least intensified by the ice loss during that summertime. So this is a long memory mechanism. Now, this is something that's been studied by a lot of people. And this is not the whole list of papers that's come out just in the last couple of years. You can see the dates there are 2014, 2014, 15. This is a very robust mechanism. It's in the models. We've seen it in the observations. It's actually occurring as I speak. So we're noticing right now that the stratospheric polar vortex is starting to break down. Judah Cohen at AER is one of the loudest voices about this particular mechanism, and he has a great blog that talks about what's going on right now. And what we see is this very thing happening. And so there's links to, obviously, the temperatures in Asia there. We think this is why we're seeing these negative temperature trends occurring in Asia. It goes back to ice loss in the Barents-Kara Sea. All right, well, let's look at the real world and see if there's evidence for this mechanism happening. And we can look at two particular winters. Here we have November of 2007. So these blue areas that I'm showing in this chart here are showing you where the ice was lost in this particular year, so in November 2007. And here's November 2014, more recently. You can see that in both cases, there was a lot of ice loss over on the Pacific side. So Alaska's in the upper left corner there. But let's look at the surface temperature. Now remember, this is in the Pacific. So the idea then, as I talked about in my It Takes Two to Tango, is if we have ice loss there, then there's the potential for an interaction with the jet stream if we get a ridge forming in the right place. So in 27, it was part of the negative PDO phase. And if we look at the surface temperature anomalies over North America for that winter, so this is January, February 2008, following that ice pattern in 27, we don't see a big, interesting pattern happening that year. That was a negative PDO year. In 2014, we see a very different story with very similar ice loss conditions. And the difference here, again, is because we had these two phases of PDO, or at least that's my interpretation of what's happening. We had the positive PDO happening in 2014, and that allowed this It Takes Two to Tango mechanism to kick in because we had the ridge favored in that location where the sea ice loss could intensify it and contribute to this very persistent pattern of warm anomalies in the west, cold anomalies in the east. We have evidence from models to support this idea. So this paper that came out just last year, I think is a very interesting one. It focused right into the year of the polar vortex, the winter of 2013, 2014. So what I'm showing you here now are the observed 500 millibar height anomalies. We're looking down on the North Pole. North America's off to the right. We're kind of focused on the Pacific sector here down on the bottom. And what you see is what you remember from that winter is a very strong ridging, the ridiculously resilient ridge over the west coast that Tim talked about. But you also see that terribly tenacious trough over North America downstream from the ridge. All right? These are the observations. So what this group did, Lee et al., was they took an atmospheric model and they forced it with the sea surface temperature patterns that occurred that winter. And they ran it over and over again so they could get good statistics. And here's what they got in terms of 500 millibar height anomalies when they only changed the Pacific sea surface temperature. So remember, this is went right after the shift to the positive PDO. And what they found was positive height anomalies along the west coast, a little bit also on the Asian side, but it doesn't really look much like the observations. So then they forced the model with only the sea ice conditions that year to see how just the ice itself, the ice loss itself, would affect the atmosphere. And they found, again, an area of positive height anomalies right in the Bering Sea. So when you put these two together, the sea surface temperature anomalies and the sea ice forcing the atmosphere, you get a response that looks very similar to what actually happened. So what this says is that it's not just natural variability, which some people are suggesting, and it's not just the sea ice. But when you put the two together and they coincide in terms of where the ridge is and where the ice anomalies are, then you get these persistent ridges like we saw. And also when you put the two together here, you can see the result also intensifies that terribly tenacious trough over the east. There's a lot more work to be done on this, but I think the evidence is starting to show that it looks like a pretty robust linkage. All right, shifting to group 3 here, category 3 of research, and this is the shortest and most, I'd say, tenuous. And this is whether there's some impact of what's happening in the Arctic on sea surface temperature patterns and how that might be affecting the jet stream. So this is an amazing picture from just last month. This was the storm named Frank that hit the UK. It was one of the worst ones they had in December. And again, we'll take a look at what was going on in the North Atlantic in terms of sea surface temperature anomalies. And again, we see this cold blob of temperature just south of Greenland and Iceland. Those temperatures or those anomalies are running up over 2 degrees, which is pretty big for the ocean, and you also see those warm temperatures off the east coast. So there's a paper that came out just a couple months ago by Rahmstorff et al. Suggesting that in their analysis, the meltwater, the extra meltwater that's coming off of Greenland, both the surface and also the undersides of the ice shelves, are contributing to this lens of cooler, fresher water that's sitting in the North Atlantic right now. So let's think about how that cool pool, getting to your question earlier, how that might be affecting the jet stream. Now think about how it's affecting the gradients in this area, all right? So we have this cooling happening, and we have a lot of warm anomalies to the south. So that's setting up a stronger gradient, right? This should have this should contribute anyway to a jet stream that is shaped somewhat like the anomaly itself, because that's where the gradients are strongest. Remember, this is adding on to whatever's there, so this is a contribution to the jet stream. Well, let's look at what the actual jet stream looked like during Storm Frank. It looks a lot like that, and it's looked a lot like that through that whole month of December, with a big trough basically encircling that pool of cool water. Now, this is all just circumstantial evidence, but I think it's very suggestive of how this cool pool might be favoring this kind of a jet stream pattern going into the winter, because that cool pool isn't going to go anywhere anytime soon. Sea surface temperature anomalies that big and that expansive don't go away overnight. So, wrapping up here, what can we expect this winter?
Washington last night?
I think it's the future, right? The next few days. Yeah.
So that's a picture of Friday night?
Could very well be. Could very well be. Yep. what's the Beltway, right? So my interpretation is that we're sailing in totally uncharted territory. And as we go back and look at, again, the surface temperature anomaly pattern, we've seen this map several times or something like it during this week. It's a very interesting mess. So this is for the average for last month, last December, all right? And let me point out some features here. So obviously we've got El Nino going on, right? Big, strong El Nino. And El Nino all by itself, if you think about gradients, you know, I'm always thinking about temperature gradients and how they're affecting what the upper level flow is going to look like. And El Nino all by itself generally strengthens the tropical jet, right? Because it's this warm tongue and it's causing that poleward gradient to get stronger. But what we have in place this year that we haven't had before with other El Ninos is this warm blob. This area of very warm water that's been sitting up in the northeast Pacific basically since late 2013. And it is basically reducing that effect of El Nino on the Pacific jet in ways that we're not really understanding very well yet, in my opinion. And then we have the cold blob here. We already talked about that. And we have this incredibly warm Arctic. So we've got this cast of characters on the stage that have never played together before. Some of them are natural, like El Ninos. We've had those before. Warm blob, I don't know. There's a lot of evidence that this is a warmer blob than maybe we've seen in at least a long time. It's causing a lot of impacts on the ecosystem in the Pacific. You've heard of sea lion pups being starved because the upwelling along the west coast has been shut down. We've got algae blooms, toxic algae blooms all up and down the west coast. I mean, all kinds of things are happening as a result of this warm blob that really haven't been seen before. Do you have a question?
I just had a comment on that. Actually, in 1997, that signal was there, but as you said, you could actually derive that signal through EOF. It's I think it's called the North Pacific mode. Mm-hmm. It's a 30 EOF.
It's similar to the PDL.
Yeah, it's similar. But actually, as you said, we were in a record strong state of that signal back in June, and it continued through the summer. So I just wanted to comment on that.
Yeah, but if you compare the Pacific sea surface temperature anomalies in the 97, 98 El Nino versus this one, the warm blob is much, much, much stronger now than it was then.
Yes, right.
Cool blob was not there, and the Arctic was nothing like what it is now. Yeah. Yeah, Phil.
One thing I've been talking about a lot is this year, it seems the warming is very northern hemisphere focused. Even with the El Nino, we haven't seen the warmth kind of bleeding down the west coast of South America like we normally do. And I'm just kind of curious as to why, if you have any thoughts as to why it's the northern hemisphere is so stinking warm, and the southern hemisphere, while a little warm, it's not the typical kind of canonical El Nino temperature patterns that we see.
Exactly. And we don't have amplified Antarctic warming. The southern hemisphere is behaving very, very differently from the northern hemisphere in terms of how the anomalies are showing up. And in fact, the southern hemisphere polar jet is getting stronger, not weaker. So, there's just a lot of really interesting regional changes that are going on that I think are yet to be explained. I mean, I think the southern hemisphere jet, we have a pretty good idea of why that one's getting stronger. We could talk about that later if you want. But, my point is that there's just a lot of things going on that we've never seen happen together before. And so trying to predict what's going to happen this winter, and we know that the impacts of El Nino really don't start till January, so the strongest ones. We're in for a very interesting winter for sure. And there are some forecasts for what the winter is going to bring. This is the forecast put out by Judah Cohen at AER again. He does something similar to what Phil was talking about yesterday, a very statistical, looking at different factors that play into different patterns in the atmosphere in both Eurasia and also North America, and coming up with a statistical system for trying to predict what's going on. One of the biggest factors that he looks at is how much snow there is in Eurasia in the fall, in October, and how rapidly that snow moves southward. So this is his forecast for January, February, March of this winter. And let's compare that to what NOAA's forecast looks like for North America. And, it looks pretty similar in the west, but this area in the northeast, which, is a pretty high impact area, looks totally different. So it's going to be very interesting to see how this bake-off comes out this winter. I don't think NOAA takes into account what's going on in the Arctic in putting out their forecasts.
Well, they'll learn something, though, won't they?
They could very well. Or maybe Judah will. We'll see. All right. So here we are this year. This is what the sea ice anomalies look like in this past November. And I keep showing you November because that turns out to be the month that has the strongest relationship with winter patterns. So we had a lot of ice loss over on the Atlantic side, over in that Barents Sea area. And you remember that was linked with cold temperatures in Siberia during the later winter. And we also have quite a bit of ice loss over in the Pacific side. So what I want to look at now, how's my time doing, is the forecasts for the jet stream for the next couple weeks. And this is put out by the University of Washington. Maybe you guys have looked at this before. So North America is down on the bottom there, and this is going out 2 weeks from today. And I think there's some really interesting features to kind of focus in on. One is the ridge that just won't die off of the west coast of North America, or right over California, really. It gets squelched by a low now and then, but it just keeps popping up. We also see the jet tending to split right at the west coast. So we see the subtropical jet coming in, and we see the polar jet doing something completely separate. Now think back to El Niños of influencing that subtropical jet for the most part, but the polar jet may be responding to other factors, the blob, the very warm Arctic, that ice loss up in the North Pacific. So I think that's an interesting thing, that we see that ridge just won't die, even though we have this very strong El Nino. We don't see the typical Pineapple Express type pattern showing up in the eastern Pacific. Yeah.
Dr. Francis Howard, Forensic of USA Washington. Given what's coming in the next couple of days on the East Coast, seems to go exactly with what you're saying. We're getting some phasing here due to the split flow. Would it be normal to think that this could happen a few more times this winter, given what's going on right now?
Well, that fits very well with what Judah Cohen's theory would be. We're seeing this disruption of the stratospheric polar vortex happening. We've seen a very negative Arctic oscillation in the last week, and being projected to stay pretty negative for a while. When it's negative, it tends to be associated with a very wavy polar jet, especially over North America and across the Atlantic and over into Europe. And that seems to be what's panning out.
I just think about last season when the folks in Boston had all their snow fatigue. If we're getting now toward February and March, where we're even more active and stormy, just thinking ahead.
I'm always thinking ahead like that too. And so, and the whole idea is that, we get this pattern set up. The individual storms are riding through that large wave pattern, right? And that's something that people kind of get confused about sometimes, where, you've got these planetary scale waves, but the individual storms themselves actually move through those waves. So, it does look like it's starting to set up more like a last winter-ish kind of a pattern. And again, you see this very, very wavy pattern continuing across the Atlantic over into Eurasia. Just saying. Okay. So just to kind of summarize, here we have the thickness anomalies, 1,000 to 500 miles, thickness anomalies over the last decade and a half, looking down on the North Pole. Clearly, those anomalies are much, much bigger over the Arctic. This is a clear signal of this amplified Arctic warming. we really think this is creating these weakened westerly winds in the upper levels. We see this in the OBS. We see models supporting this idea. And really, the link that we're still trying to fortify is whether that is causing the upper level jet to either have bigger waves or have these wavy patterns more often. And we definitely have some evidence that seems to support that now. And we know that if that's the case, we're going to get these much more persistent type patterns like we saw the last couple of winters, like we saw in 2012, but with the exact different phasing of where the troughs and the ridges were located. And we know that when that happens, it can lead to the kinds of extreme events that are related to very persistent weather conditions, whether they be cold, dry, wet, hot. But there's this big question mark hanging out there that is very much hot research, and that is how this sort of new factor in the system, that is this very rapidly warming Arctic, is going to play with the natural fluctuations that we know about in the climate system, things like the PDO, things like El Nino. How these interactions are going to occur, I think, is still going to be the topics of many, many research papers to come. So, once again, it's so great to be here. Thank you so much for asking me back, Dave, and I look forward to some questions.
Thanks very much, Jennifer. We do have some time left, about 10 minutes or so for questions and discussion. So just please, in the room, just raise your hand. We'll make sure you have a microphone. Identify yourself. And if those of you online have any questions, you can submit those too. But I do want to remind everybody that we're going to be bringing Jennifer back, and also Dr. Ben Preston, who's going to be the next speaker at the end of the second session to answer internet questions. John?
Dr. Francis, this is John Morales from NBC in Miami. So let's tie in a little bit of Dr. Klotzbach's talk yesterday regarding the persistent troughiness in the western Atlantic, a big dip in the jet stream over the last 10 years or so that's been observed. You showed as well the slowing of the zonal flow in that area too. But now we add in this colder North Atlantic factor, which, if I understand your presentation correctly, you're telling me that that should speed up the jet stream there and possibly make it troughier near Greenland as opposed to a ridge near Greenland. So which one is it? What will happen?
Yeah, well, you know, there's two parts to that. So that cool pool should be favoring the troughiness over, you know, sort of more towards the eastern Atlantic, I'd say. But we're also seeing a lot of ridging happening over Greenland. In fact, there's a Greenland blocking index that people are monitoring, and that has shown a major uptick in the last 10 years, I'd say. So much more frequent blocking happening in the North Atlantic, especially near Greenland. And so, you know, you can picture that is a pattern, right? Kind of a continuum there. So if we have a lot of ice loss in the Atlantic sector of the Arctic, that we think should intensify and perhaps contribute to that uptick in the Greenland blocking index. And then the cold pool is doing its thing, perhaps linked up to the Arctic through that extra meltwater from Greenland, which is part of the story of the Arctic unraveling. You know, shifting maybe the focus of where the blocking's happening a little bit, but certainly having a big impact on the UK. But this is another example, I think, of how these perhaps natural fluctuations, such as the change in the Atlantic meridional overturning circulation, which is what Phil talked about, which is part of the natural cycle of sea surface temperatures in the Atlantic, being perhaps amplified in its negative phase by this melting of Greenland meltwater. So I think it's a fascinating topic that's going to get studied to death. But yeah, it's complicated and really interesting.
I mean, just as a follow-up, well, you're going to add something too, right,
Go
Phil?
ahead.
No. I mean, to boil it down for my audience online and whoever's watching the live stream, you would expect the Western Atlantic or Eastern U.S. to continue to be troughy. That's what you're saying.
All indications are for this winter to have that pattern, yes. But, you know, El Nino's going to throw a big wrench into the works. And I think that's why I said we're in uncharted territory. I don't think there's an easy answer out there, but from what we're seeing, what's happening in the stratospheric vortex right now, which is consistent with this hypothesis that I showed you, how that ice loss in the Barents-Kara Sea tends to increase the amplitude of the wave over Europe and Asia, and that leads to the stratospheric vortex breaking down, which perpetuates the wavy polar jet stream later in the winter. So that seems to be playing out. But we didn't have an El Nino for the last couple of decades, really, to factor into this.
I just had a question regarding the kind of the melting of Greenland, and in terms of kind of its impacts on the salinity, if that's the primary driver of this meridional circulation.
Mm-hmm.
Do you find that the melting of Greenland's ice, that is it kind of uniform around, like say like the southern part? I'm just thinking, like, if you're looking for, say, like salinity drops, would you look like on the west coast of Greenland, the east coast of Greenland, or is it kind of uniformly spread?
It varies from year to year depending on where the the circulation brings in more warm air and more moisture, and where the clouds are having an influence. I mean, it's a complicated set of factors that cause the melt to happen in one place over another. But it's really the melting along the east coast of Greenland that would be contributing to the cool pool, because if you have melt along the west, it tends to get carried away by the Labrador Current that basically moves northward along the west coast of Greenland and then down south along North America.
Dr. Francis Mazzafino from KGW in Portland. So looking ahead, let's just skip over the rest of this winter because it's very complicated. But if, let's say, the warm blob in the Pacific goes away, El Nino goes away, we're in a positive phase of the PDO, would you then expect to see a pattern like we saw the last couple of winters with a lot of ridging in the west and a lot of troughing and cold in the east?
Well, that's what the research is suggesting, that when we have a positive PDO like sea surface temperature anomaly pattern out in the Pacific, that favors ridging in the west, troughing in the east. And then on top of that, if we get more ice loss in the Pacific, which there's no reason to think that the ice is going to rebound anytime soon, I think we could definitely see that kind of a persistent pattern showing up again. And until the PDO flips, the warm blob, I think, is sort of tangled up with the PDO to some extent. It's probably PDO plus anthropogenic sea surface temperature warming. Until it flips, I don't think we're going to see a persistent shift.
Howard Bernstein, Washington, WSA-TV. Little bit different. You mentioned the subtropical jet strengthening, and I know your focus is on the Arctic, but we had some really impressive flooding events this year, like in Oklahoma, Texas, and South Carolina.
Yeah.
And I lived in New Orleans for a few years, and when that subtropical jet was kicking, I mean,
Definitely.
it was dumping. Do you anticipate, because of these changes, that these high, extreme flooding rains that we've seen, events, that would become maybe more commonplace?
Well, just forgetting about El Nino for a minute, just knowing that there's more water vapor in the atmosphere, and that's something we've measured increasing by about 7% since the 70s, then that all by itself, and it's been measured, those heavy precipitation events have been increasing. More so in the eastern United States than in the west, but overall, yeah, I mean, there's more water vapor to work with. But when you get an El Nino situation where you're intensifying the subtropical jet, that's going to increase the dynamics. It's bringing more moisture in from the Pacific, that very warm water out there. So, those things combined are leading to these extreme events that, we keep using unprecedented and record-breaking, and, it seems like we're breaking records every week.
So you think it'll make Dr. Klotzbach's job easier? Knowing he's going to have a more persistent subtropical jet on a regular basis?
No, because El Nino's going to flip back to La Nina probably. So, not necessarily.
Jim. Jennifer, Jim White, University of Colorado. A fantastic talk. Thank you.
Thank you.
So, it's a question about the future. Where, as you pointed out, the Arctic is set up to lose summer sea ice pretty much across the Arctic, with the exception of old ice that's piling up in the northern Canadian islands. what happens when you have even more blue water out there? What does that do to the jet? When you lose this pattern of mostly having lost it in the west, and now it's going to be pretty much lost across the Arctic?
Yeah, well, we'll always have winter ice, or always, at least for as far as we can see. So it's really about where we get the extra warming happening in different regions of the Arctic. It's going to vary one year to the next. But as you say, if we lose enough of that summer ice, so basically the whole Arctic Ocean is just way warm in the summer, and you don't have this regional influence like I was talking about, then, probably wherever you get a ridge forming, you're going to have it be more intense than it used to be. It affects the ridges, right? Because that's where the jet stream interacts with this extra warming. So it'll be less regionally predictable, perhaps.
All right, great. Jennifer, thank you so much. This has been terrific.